Hey there, awesome physics students. Let's talk about some of the various forces that we're going to use in our force analysis with Newton's laws. We're going to talk about the normal and friction. Let's start with the normal force. First of all, the name normal. The name doesn't mean your sort of typical, ordinary, everyday kind of force. Normal in this sense means perpendicular. We're using it in the mathematical sense. And so this force tells you the direction in the name. The direction is perpendicular to the surface. So if you have two objects, we know that objects are solid. They don't pass through each other like ghosts pass through walls in movies. The force that prevents them from passing through each other is the normal force. So for example, if you took your hand and pressed it up against the wall, your hand is going to feel, the wall is going to put a force on your hand. Your hand's going to feel a force that's perpendicular to the surface of the wall. Okay. If on the other hand you took an object and you, like a box, and you put it on a ramp, and that ramp was at an incline, the box doesn't want to go through the ramp, and the normal force then is going to prevent that and will act perpendicular again to the surface at a 90-degree angle to the surface. Another useful example here is a bathroom scale. If you stand on a bathroom scale, your feet don't want to go through the bathroom scale because they're both solid objects, and so the force that prevents that from happening is the normal force. The scale actually reads the normal force. We look at it and we interpret it as our weight, and it is your weight under certain circumstances, but in more general terms, it's the force. What the scale reads is actually the normal force. That is the force with which the scale is pushing on you to prevent the surfaces from going through each other. So that's the force on you from the scale. If you put the scale on an incline, it would be at an angle there, and it would no longer read your true weight. Of course, no one weighs themselves like that in the morning for obvious reasons. What is the origin of this force? Well, if you look in detail at atoms, so for example, if you think of yourself, if you take your hand and you touch a table, push on the table, you feel that normal force with your hands. What's really going on though is that your hands and the table are both made of atoms, and atoms have protons and neutrons in the nucleus, and then they have electrons on the outside in the atomic orbitals. And the table too has protons and neutrons in the nucleus and electrons on the outer part of the atom. And when the electrons from your hand get close to the electrons in the table, they repel each other because they're both negative and same charges repel. The closer you get those two, the bigger the force of repulsion. That is the normal force. That's the force you feel. So if you think about this, this is really kind of cool. When you touch something, you don't actually ever touch it. What's really happening is the electrons in your fingers are getting close to the electrons in the table, for example. On an everyday usage, I mean, this is really cool, but on an everyday basis, this isn't terribly useful to keep in mind. But it is, in some cases, it's nice to know what the origin of the force is. The most practical thing we're going to use is that it's perpendicular to the surface. The symbols we usually use for normal force are Fn for force normal or normal force. Sometimes you see this for normal force, and sometimes you just see an N for normal force. Okay? Let's talk about friction. Friction, in contrast to normal, is parallel to the surface. And so what actually causes it to be parallel? Well, if you zoom in on, friction is, what you get if you take like a heavy box and you try and drag that box across the surface. If you zoomed in on the box and floor interface, you would see that while they look kind of smooth on the outside, they're actually really jagged when you zoom in on them with a microscope. And what's happening here is that the peaks and valleys in the box are getting stuck on the peaks and valleys in the floor, and they catch and slip and catch and slip, and that produces a force that's parallel to the surface. And friction, a key thing about friction is it always opposes or attempts to oppose motion. Okay? And we further classify friction into two categories. One is static friction, and this is static friction is the situation where, let's say, you're pushing on the box and it hasn't yet moved. So you push a little bit, and static friction prevents motion. So it pushes back on whatever force is necessary to prevent it from moving. If you push harder on the box, static friction will then push harder in the opposite direction, again to oppose the motion. So the value or the amount or the strength of static friction varies. Okay? It will increase and keep increasing whatever's needed to prevent motion up to a limit. And then it will start to slide. The other type of friction here is when things are actually sliding, and this is called kinetic friction. And kinetic meaning things are moving. And this one is constant. Once you get your box and your floor. Of course, you probably noticed that heavier boxes are more difficult to move than lightweight boxes. And the reason that is that the force of kinetic friction depends on how hard the two surfaces are pressed together. And heavier objects are going to be pressed against the floor with a greater force than lighter objects. And that force that they're pressed together with is actually the normal force. It's not gravity specifically. So if you took, for example, a lightweight object and you pressed it against a wall with a huge force, it wouldn't want to slide against the wall. It'd be very difficult to drag it down the wall. And if you pressed less and pushed it against the wall less, then it would be easier to slide. Okay. Oftentimes we use the symbols Fs for static friction, Fk for kinetic friction, and sometimes you see friction just written like this. All right.